Hello student, the last class we discussed the different problem related to the solid state. Now focus on the last part of these chapters, and it is also very important, the defects of the solids. And in defects or imperfection of the solid, so it arises due to irregularities of the arrangement of the constituent particles in the solid, constituent particles in the solid. So this way you have to understand it. So that means it arises due to irregularities of the arrangement of the constituent particle in the solids. So that means the constituent particle in the solid, it can be atoms, it can be ions, it can be molecules, whatever it is. So that means the constituent particle, their irregularities will be there in their arrangement, and because of that what phenomena arises in a solid, that is called as a defects or imperfections. The defects can be classified into two categories. Defects can be classified, generally we need to know that defects can be classified into two categories. One is the atomic defects and one will be the electronic defects. Our focus will be the atomic defects, and in atomic defects our focus will be in point defects. And point defects, there are two categories will be there: stoichiometric defects and non-stoichiometric defects. And in stoichiometric defects there are two categories we have to study, three things we have to study. One is Schottky defects, one is Frenkel, and one is impurity. One is Schottky, one is Frenkel defects, one is impurity defects. And non-stoichiometric, mainly two defects we have to study, and one is nothing but a metal deficiency, and one will be metal excess. This type of defects you have to study. Now you look at in stoichiometric defect, first you have to study the Schottky defects. What is Schottky defects? Then Frenkel defects, then impurity defects, then metal deficiency and metal excess defect. These are the things we need to study over here. So then if you look at nicely over here, then you will understand clearly in Schottky defects, if you look at in Schottky defects, what will happen in Schottky defects? So in Schottky defects, what will happen, you understand clearly. In Schottky defects, what will happen, my dear? In Schottky defects, this is a stoichiometric defects. If I write down the defects, I write down the solid structure, cation and anion, especially for the ionic solid, this type of defects will be arises. Suppose this is cation, this is anion, this is cation, and this is anion. And the next one will be nothing but an anion, and then this will be cation, and then this will be anion, this will be cation. This is a solid structure. Now this will be cation and this will be anion. Now this one is missing, and this is a cation, and then this will be anion. And now the next one, this will be anion, and then this will be cation, and then this will be anion, and then this will be cation, and this one is missing. Now you look at this scenario, if you look at this solid structure, that one cation, here one anion is missing, and here one cation is missing. So that means this type of solid, if you consider in Schottky defect, from their lattice structure, in the particular positions, from the particular position one cation and anion will be missing. Cation and anion will be missing. Cation and anion is missing. Because of this cation anion missing, what is happening? Mass per unit volume will be, mass per unit volume, that is nothing but a density will be what? Density will be decreased because one cation and one anion is missing. So that is why mass per volume is nothing but a density will decrease. Moreover, as they are, as a vacancy is there, it will behave like a hole. So that means the conductivity will increase. Conductivity will increase. Conductivity will increase, whereas density will decrease. Clear? And moreover, this type of defects is formed by which one? Like NaCl, like cesium chloride, like AgBr. So generally the compound which has a comparable cation and anion site, moreover high coordination number. NaCl coordination number is 6:6, cesium chloride 8:8. So that is why generally this type of defects will be arises for that type of ionic salt which has a comparable size of cation and anion as well as high coordinations. And this type of defect means one cation and one anion will be missed from their particular lattice site, and because of that density will be decreases, hole will be created, conductivity will increase. So this is nothing but a Schottky defects. What is called as a Frenkel defects? So let us focus for the Frenkel defects. In Frenkel defects, what will happen, my dear? You look at in Frenkel defects. In Frenkel defects, what will happen? You look at, my dear, Frenkel defects. In Frenkel defects, in Frenkel defects, what will happen? In Frenkel defects, you look at the picture. Suppose cation, anion, cation, it is also for the ionic solid, and anion, and this will be anion, and here will be cation which is missed from their side. This will be cation, and then anion, and then cation, and then anion is there, then and then this will be cation, and then anion, and then cation, and then anion. So this is the picture. If you look at, this is the picture of the solid. Now this cation is missed from here and occupies some interstitial positions. Some interstitial position of the lattice, it is not there in proper place over there, but it occupies some interstitial position of the lattice. And this type of defect is called as a Frenkel defects. And because of that, this other name of these defects is called as a dislocation defects. This is called as a dislocation defects. Why? The reason is the cation is missing from their particular site and it dislocates to an interstitial position. That is why these defects also called as a dislocation defects. And then this type of salt like AgCl, like AgI, like zinc sulfide, like silver bromide used to show this type of defects. Moreover, where the cation and anion size will be big difference will be there and the coordination number will be less, that type of salt used to show the Frenkel defects. Moreover, this silver bromide is the salt, one and only salt which used to show Schottky defects as well as Frenkel defects. This silver bromide is the salt which used to show Frenkel defects and Schottky defects. So this is about Frenkel and Schottky. Let us focus what is called as a impurity defects. So then you look at what is impurity defects. In impurity defects, if you understand the impurity defects, impurity defects. In impurity defects, what will happen, my dear? In impurity defects, suppose the sodium chloride is crystallizes. With that, if other cation is crystallizes, that is called as a impurity defects. Maybe another cation is crystallizes and take the positions of the sodium. That is called as a impurity defect. Suppose if you look at, there is a Na plus is there, Cl minus is there, Na plus is there, and then Cl minus is there, and then Cl minus is there, Na plus is there, and then Cl minus is there, and then Na plus is there, and then Na plus should be over here, it is missing. Now Cl minus, Na plus, and then Cl minus, like that thing is there. Now look at, instead of these Na plus positions, maybe strontium is taking the positions of Na plus. Then when strontium is taking the positions of sodium, then 1 unit of positive charge will be more. So that is why one sodium ion will be knocked out from over here itself. You will get this type of structure. And this is nothing but a what? Impurity defects. When the other cation is taking the positions, and then depending on the charge, maybe one cation or two cation will be moved away and one vacancy will be created. It's some sort of called as a dropping. So now you look at when strontium is taking, and this is nothing but a impurity defects. Suppose if you look at one strontium is creating what? One cationic vacancy. You got my point? When one strontium is come in the positions as an impurity in the positions of Na plus, it creating what? It creating one cationic vacancy. That means one Na plus is missing from their particular positions. So that is why they can give one questions like this. So 10 to the power minus 3%, minus 10 to the power minus 3%, or they can give you like that, 10 to the power minus 3 moles of strontium chloride doped with NaCl. So then, or they can give you a mole percent, they can give you, later we can do 10 to the power minus 3 mole percent strontium chloride doped with NaCl. How many cationic vacancy will be created? So in that questions, percent means what? 10 to the power minus these things. Generally 10% means what? 10 by 100. So this many percent means what? This by 100 is nothing but how much? This many mole. This many mole will be there. You got my point? And this many mole will contain how many strontium? This into Avogadro number 6 into 10 to the power 23. This many strontium will be there. 1 mole will contain Avogadro number of strontium. This many mole will contain how much? 10 to the power minus 5 into Avogadro number. Roughly we took 6 rather than taking 6.023 into 10 to the power 23 to make the calculation easy. So then we got it over here itself like this. Now you look at this one strontium is created, one cationic vacancy. This many strontium will create how many cationic vacancy? So then this is, you can write down this into 10 to the power 18. So this many cationic vacancy will be created. Cationic vacancy will be created. This is the idea. One strontium is creating one cationic vacancy. They told 10 to the power minus 3 mole percent of strontium chloride doped with NaCl. So then this many means what? 10 more percent means what? This by 100, that means 10 to the power minus 5 mole strontium is there. 10 to the power minus 5 mole strontium means how many? Into Avogadro number, that many strontium is there. So one strontium is created, one cationic vacancy. So this many will create how many? This many number of cationic vacancy is nothing but the answer will be 6 into 10 to the power 18. Clear? So this type of problem they used to ask. So this is all about the stoichiometric defects. Then we will focus for the non-stoichiometric defects. So what is non-stoichiometric defects? In non-stoichiometric defects, what will happen? Non-stoichiometric defects. If you look at in non-stoichiometric defects, what will happen? You will understand clearly. Suppose the metal excess and metal deficiency. There are certain oxide is there which has a variable valency, like the iron oxide. The iron can exist as a +2 and +3. So they used to, some of the iron +2 is missing from their lattice side, and then some iron 3 will come into that position to maintain the electrical neutrality. That is called as a non-stoichiometric defects, and that is metal deficiency. They will give you like this formula, like this, Fe 0.94 and this, like that things they will be given. Clear? And they will ask you the questions, how many percentage of iron plus 2, how many percentage of iron plus 3 is there. Like that questions they will give, this type of things. How you will proceed? So then you will think over it. First you make a whole number multiplied by 100. This will be 94, this will be 100. And out of this 94, some amount of iron plus 2 is there, some amount of iron plus 3. How many is there? I don't know. So then I am telling let iron plus 3 is x, and then iron plus 2 will be there 94 minus x. Total will be how much? 94. Got my point? And oxide charge is there minus 2, you know. And overall molecule will be a neutral molecule. Then we can write down plus 3 charge into x, x amount is there, plus 2 charge into 94 minus x, plus minus 2 charge of the oxide, how many is there, into 100 will be equals to 0. Overall charge, if you add up all the charge, it will be nothing but a 0. The molecule is a overall neutral. From there we will get the value of x. You look at 3x plus 2 into 90, 188. This is 2 into 90, 180 and 188, and this is nothing but a minus 2x minus 200, 0. So then we are getting 3x minus 2x will be equal, this is minus 12 plus 188 minus 200 minus 12, that side will be nothing but a plus 12. We will get what? Plus 12. Then x will be equals to nothing but how much? 12. You got the value, x will be equals to nothing but a 12. So then iron plus 3 is there how many? 12. And then iron plus 2 will be there how many? 94 minus 12 is nothing but a how many? It will becomes around is nothing but a 82. So that is why if you look at that, if they told you the percentage of iron plus 3, percentage of iron plus 3 will be nothing but how much? 12 by, and out of 94, 12 is there, iron plus 3. So then into 100. Then if they told percentage of iron plus 2, 82 by 94 into 100, like that they can ask you that thing. This type of problem you have to proceed. And this is nothing but a metal deficiency, and this is nothing but a non-stoichiometric defects. Now once you understand the non-stoichiometric defect, that metal deficiency, then we will focus for the metal excess. Metal excess, there are two mechanisms is there. I will explain that metal excess defects with two mechanism. Metal excess defects, metal excess defect. This is two types of will be there, I will explain. Suppose if you are heated, sodium vapor is in NaCl and it will be there in hot conditions. When the sodium vapor will be there in NaCl in hot conditions, then what will happen, you know, the chloride from the NaCl lattice will come into the surface of sodium metal, and then it will lose the minus of electron and it will be converted to what? Na plus, and this electron will take the positions of the chloride. It's nothing but a, whenever you are taking the NaCl and heated with a sodium vapor, the electron from the sodium will go to the place of the chloride in a NaCl lattice, and chloride will come from the lattice positions of the NaCl. The picture will be like this. Suppose Na plus, and this is Cl minus, and this is Na plus, and this is Cl minus, and this is Cl minus, and this will be Na plus, and then Na plus, and next one will be Cl minus, and next one will be Na plus. Instead of these positions, suppose this position is taken by the electron, which is coming from the Na plus. Now because of this scenario, if you look at, some lattice position is taking the electron, and then this is a electron rich center. Then when it will absorb the visible light and it will go in the higher energy state, and when it will come back it will release certain light. So that is why lithium chloride used to show what color? Pink color. So like that the sodium chloride used to show certain color. So that is why this electron rich center, it is called as a what? F center. Already everybody know what is, this is nothing but what? Electron rich center is nothing but a F center. So that is why in metal excess defect, this type of scenario will appear. Another category of mechanism is there, generally the zinc oxide. The zinc oxide in whenever the cold is there, it will be white, but when you will little bit heat it up, it will be nothing but a yellow color. Why? Because the reason is the zinc when oxide when it will be heated up, it will be converted to zinc plus 2 and loss of electron will be there and it will be oxide will be there. And now in the positions of the lattice positions, what will happen, you know, some extra zinc is there, oxide is there like this, zinc is there and oxide will be there like that, and this will be oxide, this will be zinc, like that the lattice positions will be goes on. This is a lattice structure. But in the certain structure of lattice, some excess amount of zinc will be there. To balance this, the extra electron will come also into interstitial positions. And this is nothing but called as a what? The metal excess defect. So because of this electron rich, the colorations will come what? The yellow colorations will appear when you are little bit heat the zinc oxide. And this is nothing but another type of metal excess defects. So these are nothing but non-stoichiometric defects. So I explained the entire defects. What is explained is nothing but a stoichiometric defects, and stoichiometric defects, Schottky defects, Frankel defects, impurity defects, non-stoichiometric defects, metal deficiency and metal excess defects and F center. This is a very, very important. So already we discussed. Now we are going to discuss the conducting property and magnetic properties of the solid, and then only this chapter will wind up. So let us focus the conductivity properties of a solid. You know, any substance which has a conductivity value ohm per inverse meter inverse, if it is 10 to the power, any things will be there. If conductivity value 10 to the power 10 to 10 to the power 20, ohm inverse meter inverse, then this is called as a conducting material, highly conducting material. If the conductivity value is in the range that 10 to the power minus 6 to 10 to the power 4, that is called as a semiconductor material. This is a semiconductor. This is a semiconductor. And if it is below this is nothing but a 10 to the power minus 10 to 10 to the power minus 6, in that range, this is a non-conductor. Non-conductor. So these are the categories there. Depending on the conductivity value, there some category is there in the conducting material. Now in case of a semiconductor, already you will study in detail in physics, there are different types of semiconductor material is there. Germanium, silicon, these are very fine semiconductor material. Suppose if you look at the germanium is a semiconductor material, and generally there is a non-conducting material, conduction band. This is a conduction band and this is a valence band. There is a big gap will be there for non-conducting substance. And for the semiconducting material, there will be very little gap is there. This is a conduction band and valence band. This is a semiconductor material. This is a non-conductor. Non-conductor. And for the conducting material, this valence band, this conduction band and this valence band, they will be overlapped to each other. This is a conductor material. This is a conductor material. This is the idea. In case of a non-conducting conduction band and valence band, there is a huge gap, so that there will be no electron can go from valence band to conduction band. And in semiconductor material, this gap will be very low. But in case of a conductor, conduction band and valence band will overlap to each other. And now the question is, in germanium is a group 14 element, valence electron will be there. How many? 4 valence electron. Now it is this side is there group 13 element, another side is a group 15 element. Here nitrogen, phosphorus, arsenic, antimony, and here valence electron will be there in 5, and here valence electron will be there in 3, boron, aluminium, gallium, indium. Now this group 14 element, when you dope to it group 15 element, 1 extra electron will be there. Here 4 electron will make a covalent bond with the 4 1, extra 1 electron will be there. Electron is a negative charge. That is why group 14 when will be doped with group 15, it is called as a n-type semiconductor, because 1 extra electron will be there and that will increase the conductivity. and that is nothing but electron is a negative charge. That is why this is called as a n-type semiconductor. Whereas when germanium will dope to its group 13 element, one hole will be, extra hole will be there, and because of that this type of is called as a p-type semiconductor. When group 13 is doped to it, group 14 is a p-type semiconductor, and this NPN diode you will study in detail in physics. You know, lot of application is there in a transistor, so that type of things you will study in the physics. In the chemistry only up to this you have to know. So now this is nothing but a conductivity property. Now we have to focus for the magnetic property. You know, any material, any substance, they have a atoms has a nucleus, and around the nucleus electron is moving in a circular path. Because of the movement of an electron, there is a electric loop will be created, and that will generate the magnetic field. Tiny magnetic region will be created in a solid, and there are different category of the solid will be there. One is nothing but a diamagnetic, one will be nothing but a diamagnetic. Example I am giving is nothing but the NaCl and then H2O. These are the diamagnetic substance. And now diamagnetic means there is no unpaired electron is there. It will not influence by the external magnetic field. Whereas paramagnetic substance, this paramagnetic substance is nothing but that substance, you know, like oxygen, like copper plus 2, like iron plus 2. It has an unpaired of electron, and which will be influenced by the external magnetic field is called as a paramagnetic substance. Then rather than that, there is a ferromagnetic substance. So this ferromagnetic substance, they have a small magnetic domain or small region will be there. When you will apply the external magnetic field, they will orient along the external magnetic field. If you remove the external magnetic field, still that orientations will be present. That this ferromagnetic substance can be magnetized permanently very easily. Example, iron, chromium, nickel, these are the ferromagnetic substance, chromium oxide, these are the ferromagnetic. That means when we will apply the external magnetic field, their small domain will be orient like this along the external magnetic field. This is a ferromagnetic substance. Permanent magnet can be created over here. Then we need to know antiferromagnetic substance. Antiferro. Antiferro means what? When you apply the external magnetic field, then one will be oriented along the field, another is opposing the field. Along the field, opposing the field, along the field, opposing the field. Overall magnetic moment will be 0. Overall magnetic moment will be 0. That is nothing but a antiferromagnetic substance. Example, manganese oxide. Antiferromagnetic substance. Another one is there, ferrimagnetic substance. In ferrimagnetic substance is nothing but that substance, overall magnetic moment will be there when you will apply the external magnetic field. The small domain will be arranged like this. If the 2 is there along the external magnetic field, 1 will be there opposing the external magnetic field. Like that, maybe 3 is there, another 1 or 2 will be like that. That means the resultant value magnetic field will be there. This is nothing but a picture of a ferrimagnetic substance. Example, Fe3O4, Fe3O4, MgAl2O4. So these are the different ferrimagnetic substance. So these you have to understand over here itself. These are the magnetic properties of a solid. Then you need to know 2 points, and then you will finish it off. What is called as a piezoelectric substance, what is called as a pyroelectric substance. This is 2 times they ask the questions. Only what is you need to know? Piezoelectric substance. The piezoelectric substance is that substance, piezoelectric substance, piezo and pyro. Piezoelectric substance, piezoelectric substance, and pyroelectric substance. So these the things you have to understand, piezoelectric substance and pyroelectric substance. In piezoelectric substance, in an ionic solid, if you generate the electricity by applying generations of electricity by mechanical stress, by stress or mechanical force or by stress, that is called as a piezoelectric substance. And pyro means generations of electricity in an ionic solid, generations of electricity by applying the heat, that is called as a pyroelectric substance. So these two things you have to understand. In an ionic solid, when the ion displacement will be there, and because of that the electricity will be generated, when that ion displacement will be there, when you apply the mechanical force or stress, then the ion displacement will be there and that will create the electricity, that is called as a piezoelectric substance. And pyroelectricity means generation of electricity can be done by applying the heat, and these two things you have to understand. So now I describe all the points of the defects in a solid. I hope you understand, my dear student. Please go through it. Okay. So thank you very much. Thank you all.